Okay, everybody, we're going to get underway here. So we're going to be working on ideas within chapter 7, where we're looking at periodic properties of the elements. So I'm recommending that you have a periodic table that you can refer to. When we say periodic properties, what we're really doing in chapter 7 here is we're learning a lot more about what's going on with the periodic table and how we can extract information from it. Now, where we're going within the class, where the ideas fit together, our last exam, which was on chapters 4, 5, and 6, I think was probably the exam in this course that has the ideas that in some ways fit together the least. The stuff that we were doing in chapter 4 when it was, let's say, looking at net ionic equations, well, that had very little to do with what we were doing with Hess's law, which had very little to do with atomic orbitals. Each of those chapters had quite a few ideas that we were responsible for, but they didn't really stick together that well going across the chapters. We're going to have exactly the opposite story now, because what we're going to do is we're going to have about 3 or 4 chapters that really all fit together really closely. And the way that they're going to fit together is we're going to see that in chapter 6, we learned about electron configurations. Now in chapter 7, we're going to learn about the energy that's accompanying the electron configurations and what does it mean to add or remove electrons. Then what we're going to do in chapter 8, we're going to see how that leads us to understand more about bonding, how the atoms fit together. And then in chapter 9, we're going to even look more at bonding. So in a way, it's chapters 6, 7, 8, and 9, they really all fit together. And the key idea that we have, that we've used so far, that we're going to need for sure, is being able to use a periodic table to quite quickly get the electron configuration. If I think back, that's about the only idea that we're going to need from the early chapters. We're not going to be doing anything with stoichiometry. We're not going to be doing anything with dimensional analysis. We're not going to be doing anything with with molar mass, with almost any of the ideas that we had early on. In fact, some chemistry textbooks, they start the book right where we're going to be starting our discussion. So the reason I'm bringing that up is a lot of times for students, they view this as a positive because it's like a whole new set of ideas that they're exploring that are all going to fit together. So to me, it really begins with what we're talking about tonight. Let's see if we can begin to see how the ideas are fitting together, because they're going to be very cohesive as we go from one to the next. So within here, we're going to start by looking a little bit at the development of the periodic table. And then what I think is one of the most important ideas the entire semester, this idea of effective nuclear charge. Effective nuclear charge is really important for all of the subsequent parts of this chapter. So I'm going to connect it to ideas of the size of various atoms and ions. We're going to use effective nuclear charge to begin to understand that particular property. And in fact, we're going to use effective nuclear charge to understand pretty much all of the properties that come later on. So that was a topic within the pre-class video that I'm going to revisit, and then we'll build on that a little bit. So I pose here, this would be a typical question that I would find in chapter 7, where which of the following is the smallest? Hydrogen atom, hydrogen anion, helium atom, or helium plus cation? Now, when we're seeking to answer this, to me, we really have to have a good understanding of effective nuclear charge. And I'll show you why within class tonight. Now, another thing to bring up is within chapter 7, in terms of the format of the questions, there are formats of the questions where you're going to be asked to make predictions. There's also going to be questions where you're going to be asked to provide explanations. So this idea of predictions versus explanations, let me send you a polling question on that. Would you say, do you understand the difference between something that is a prediction and an explanation? Now, you might say yes or no, or you might say, yeah, I think I do, but I'm not sure what it means in a chemistry class. So those are coming in, almost everybody's in one of 2 categories here. Take about 10 more seconds. So what I'm seeing here is that folks think, yeah, that's something they understand, but perhaps not understand it for how it's going to show up within a chemistry class. I think that's how I would be responding to it as well. The idea here is that this would be an example of making a prediction. You're somehow taking the ideas and you're trying to apply it. I think so far we've been making a lot of predictions. We've been doing rankings of different things. We've been deciding which of these would be different from the other. An explanation is one where the information will be given and then you have to explain why. So in a way, it tells you the phenomena and then you have to say, well, this is why it's occurring. And the reason I'm bringing it up is in this chapter, especially for the properties of the elements, the effective nuclear charge is going to be part of so many of the explanations. So we want to get a good understanding of that. So let's start with a look here at the periodic table. So two people I want to associate the periodic table with would be Mendeleev and Moseley. I took some images here. These are straight out of the textbook. So we see a figure of the periodic table of Mendeleev there on the left. So he was grouping the different elements that were known in his era based on their different physical and chemical properties. And so his era was the mid 1800s, around 1860, so around the time of the American Civil War. And so he put them into different columns based on these periodic properties, which meant like repeating properties. What was interesting here is he wasn't just making a list. He wasn't just listing them alphabetically or, I don't know, based on color or something. He put them into this organizational scheme. And that led him to be able to predict the discovery of new elements. And by predicting them, he left a couple blanks in his periodic table. But he said, okay, I know the type of element that you're going to discover and put there. And so that was really what was dramatic. It wasn't just a list. It was something that allowed him to make predictions about the discovery of future elements. And so if you step back for a second, imagine how different this changes the world here of chemistry. So they were discovering elements well before Mendeleev. But notice once you have this table, how it changes everything. So let's say we're discovering different species of animals. Let's say we're discovering different types of birds. We say, oh, we've discovered this type, and this type, and this type, and this type. How many birds are we going to discover? Well, it might be an infinite number. We might just keep discovering different types of birds. There's no way that we've constrained how many would be there. Mendeleev, though, takes this and he organizes it. And he said, oh, you know, you're going to now begin to find more birds that have beaks like this. You're going to find birds that have this characteristic. So imagine that organizational scheme. Like in biology, there is no organizational scheme like that. They can keep track of what they found, but it doesn't constrain the information the same way that Mendeleev's table did. This would be a description here. This is the from the book as well that shows the different elements that we now know. I've seen a couple questions on exams sometimes pertaining to this figure right here. So let me talk through a couple details within this. So first of all, we see that at the bottom, it lists when different elements were discovered. And we find that a lot of the ones at the bottom of the periodic table, those are quite recent. Some of them, in fact, are man-made that involve nuclear chemistry. If we look over at this region right here, the text says that the majority of elements that we find in nature are readily found as compounds. They're not as distinct elements in their elemental form. So in order to discover those, we have to isolate them. We have to get them away from the other things that they're in a compound with. If you look at the ones that were known since ancient times, something like silver, gold, mercury, lead, those are things that in their elemental form, you can just find, if you're lucky, a chunk of gold, right? You're finding it in its elemental form. Not so with like these alkaline earth. If we think about these, if we connect it back to the activity series, notice those, they are very easily oxidized. You know, I don't think, unless it's in a science lab, I've never seen a piece of potassium because it's always existing in its ion form. Same thing with sodium. Outside of a chemistry lab, I've never seen a piece of sodium, but we have sodium ions all the time. That's what it meant of saying these were very reactive and they had to isolate them and get them away from the compounds that they were found in. If we look at our noble gases, those were not on Mendeleev's table. Those were not known in the 1860s. Now, there's a picture of Mendeleev. How do you think he felt when they said, hey, you know what, Dmitry, your table is incomplete. We are beginning to find new elements, and they're an entirely new column that you didn't predict. What does Mendeleev say? Well, he's a grumpy Russian. He's not happy about that. He doesn't believe it. But sure enough, they were then discovering ones, not because they were very reactive, but because they were very unreactive as gases. Sometimes I discuss with the students a little bit, well, how do you even find a gas? You know, it's not like you can just pick it up off the ground. And one time a student had this really insightful way of saying it. They said, a gas announces its presence by reacting with other things. And I just had to stop and just say that's just poetry there. I love the way that you're describing it. Indeed, a lot of times we have a reaction of gases with something else, and that's how they announce their presence. And if you've got unreacted noble gases here, then you weren't going to be able to find them easily. One more to add to our list right there, which I find interesting, right at the top here with helium. So helium, it's named for Helios, the sun god. For a while, it was my favorite element. It's not my favorite element right now. I'm a little fickle. I've moved away from helium, but for a while, it was my favorite element. I like it because it's the only element that was discovered off of planet Earth before it was discovered on our planet. And the way they discovered it was they looked at the emission spectrum of the sun. Same kind of thing that in terms of its line spectrum. And they saw new lines there because the sun is almost all hydrogen and helium. And that's how they saw new lines there. And that's where the name comes from, Helios, for the sun god. So within this one right here, this was his initial periodic table. Now, this might be one. I don't remember if this question was in the pre-class video or not. I'm going to pose it to you as a polling question. What information do you think Mendeleev would have used to group the elements? Things like the electron configuration, the boiling point, number of protons, or all of these? What do you think? Now, I find within this, I'm going to end the poll within this idea of the boiling point being the only one, because if the grouping here was based on chemical and physical properties, a boiling point would be a physical property. Electrons, protons, those were not known at the time that Mendeleev put together his table. So even though we have within this that I would say a pattern, we've used the periodic table to get some insight into, let's say, the electron configuration. That's not what Mendeleev was doing. So let's see if we played this out logically, though. He had his order that he put together that was summarizing different physical and chemical properties that he was aware of. We've just seen in chapter 6 that the periodic table also gives us a pattern that we can use to determine the electron configuration. So if I bring those two together logically, there must be something about the electron configuration that leads to these different physical and chemical properties. He didn't know about the electron configuration. He doesn't know about electrons, but we do. That's going to be a major point of this chapter. We're going to try to learn things that Mendeleev did not. We're going to try to connect the electron configurations that we saw in chapter 6 with the resulting properties that these atoms have. In fact, that's going to be everything that we do in chapters 7, 8, and 9 are all looking at that. And in fact, the rest of the semester is really this point right here. That's where they're all fitting together. So the other person we associate this is Moseley, Henry Moseley. He's sort of a tragic hero in my story. So there's a picture of Moseley. He was working with, was it Rutherford? It's one of the two. It's either Rutherford or J.J. Thomson. I think he's working with J.J. Thomson at the time. He's doing his experiments, but if you look right there at the year 1913, he's a very young British physicist, not that much different in age from you all. He volunteers for the First World War, and he quickly dies in the trenches. So he's a tragic hero who died far too young. So his experiment that he was doing here was he was directing high energy electrons at different metal surfaces. And he saw that they emitted X-rays with certain characteristic frequencies. And we associate then the atomic number with the number of protons for each of these particular elements. So he somehow figured out, based on the emission that they had, how we could think about that as far as the number of protons. And in the pre-class video, I tried to connect this with this idea of, well, how do you get X-rays at all? If you go to the dentist, how do they generate X-rays? How does that work? And the phenomenon is this. And so again, this is a little bit of review from the video within that, where we saw before in chapter 6, this emission spectrum for hydrogen and how it was related to the electronic energy levels. And that we had a large gap between levels 1 and 2, or in fact, any one where the final level was 1, that was giving rise to photons that were in the ultraviolet. Between levels ending in 2, that was visible. Higher than that, it was infrared. This was related to the idea how for hydrogen, the energy levels were degenerate, the same value based on their N value, and that they got closer and closer together as the N value increased. Here would be the energy levels for a multi-electron atom. So I'm trying to show how they're getting split out. They're getting split out. The degeneracy is being removed. And I'm also showing that they're moving lower in potential energy. They're moving lower in potential energy because I have more and more protons present. We got to be thinking about how positives and negatives attract. So with more protons, those energy levels are being pulled lower in potential energy. And in fact, another phenomenon that's taking place is the gap between these energy levels is increasing. The gap between levels 1 and 2. So the way that you get X-rays within this is you shoot in like high-speed electrons that would promote an electron from the N equals 1 level to a higher state. You've got a large gap now between, let's say, 2 and 1. So when the electron now comes back down, a photon's emitted. And the gap here is large enough for the metals that you get an X-ray being emitted. That's how they make X-rays. So this description right here, this is in a way how Moseley's experiment was working. You're not going to have to describe Moseley's experiment at this level. If you associate Moseley with atomic numbers which correspond to the number of protons, I think you're in good shape. The reason I'm bringing this up here, though, is I want us to begin to think about the importance of protons. How we have these energy levels, the electronic energy levels, they're shifting their position as we have more and more protons being present. This interaction between the electrons and the protons, that's crucial here in chapter 7. In chapter 6, we had the electron configurations. We didn't really talk about the number of protons there. Now we're going to be thinking about the number of protons that we have as well. So we're getting to the point here of the effective nuclear charge. One of my favorite topics because it explains so much for us. So at the top there, I give a equation that we can use to calculate the effective nuclear charge. In this expression, Z stands for the atomic number, that's the number of protons. So we have the effective nuclear charge, Z effective, is going to be equal to the number of protons minus S, which is a shielding term. Now, I have found that when I describe this, when I say effective nuclear charge, I never say the word Zeph. I never say effective nuclear charge is Zeph, Z-E-F-F. But I find students say that all the time. I don't know if they heard that in high school or something, but I don't think it does them any service. I don't think it helps because I don't know if they realize that Zeph is the effective nuclear charge. I find the word is so descriptive, the phrase is so descriptive. Let's try to use that. I'll stick with calling this effective nuclear charge. I'm not going to call it Zeph. Now we're going to see that many of the properties are going to depend on the electron configuration and how strongly these outer electrons are attracted to the nucleus. This attraction between the charges, we saw that a little bit back in chapter 1 when we were looking at the attractions between opposite charges, and then more in chapter 5. So what gives rise to then this attraction, the degree of the attraction? I think that the attraction is easy to understand for hydrogen because we just have one proton, one electron. Those are the only two parts that we have present as far as what's giving rise to the resulting attraction and the energy levels. But as soon as we move beyond that, it gets more complicated. We're going to have attractions between the protons and the electrons. We'll have repulsions between electrons with other electrons. And we're interested then in the net attraction that a particular electron experiences after you account for the number of protons, but then also how that attraction is somewhat diminished because there's also repulsions present as well. That's what we're going to spend some time trying to understand. The book has this analogy here that I think is a useful one. In fact, I've even seen exam questions on this, where the exam question was like, explain aspects of this analogy. So it's setting it up where they've got a particular light bulb that's now encased in this frosted glass, and you've got an observer outside of it. So let's say, I mean, imagine for a second, you are this eyeball, you're this observer on the outside. What would affect how bright or how dim that light bulb appears? I think it depends on your vantage point there. You could have maybe the light bulb itself could be turned up to a higher or a lower power. You could change the brightness of the light bulb itself. Another factor is you could change the way that it's encased in this frosted glass. Those two variables, the light bulb's brightness itself and the manner in which it's encased, that's what this expression for the effective nuclear charge is. Z in this analogy, number of protons, is like the brightness of the bulb. And S is the shielding, the manner in which it's being encased. I think that sort of breakdown, it's something I keep in mind when I'm now trying to take this and connect it to chemistry. It's going to be easy to determine the Z part, the positive charge, because that's just the number of protons. That's what Z is. When we're looking at the shielding, there's different ways that we can count to get that shielding value. And I noticed within the pre-class video, by far the most prevalent question was, how do we get shielding? How do we get the shielding one? The simplest approach for us is we're going to count the core electrons, which are those with a smaller n value, a smaller principal quantum number. Those are going to be the shielding ones. They're going to shield other electrons that are further away from the nucleus. And we can calculate this effective nuclear charge for any electron that we want in the atom. So I'm going to work through a couple examples here. So let's see if you can follow through this. And so within this one, when it comes to effective nuclear charge, we want to really completely understand the idea. We want to be able to do these calculations, and we want to be able to understand their significance. We want to completely understand this idea. So here I show how I'd calculate the effective nuclear charge if I'm looking at a hydrogen atom or a helium atom. So hydrogen is number one proton, that's what Z equals. The electron configuration would be 1s1. What would be the effective nuclear charge acting on that? There's one proton. There's no other electrons shielding it. So I'd say the effective nuclear charge on that electron in hydrogen is +1. For helium, very similar, but now I have two protons. The electron configuration would be 1s2. The effective nuclear charge acting on either of those electrons would be there's two protons, there's no shielding electrons, and it's +2. When I say no shielding, the simplest way that we can, again, estimate the shielding is to count the electrons that have a smaller n value. There is no smaller n value than n equals 1. This would be sort of my picture for each. If I was trying to make like a model of some kind. Hydrogen would have +1 for in the nucleus, and an electron and a 1s orbital around it. Helium, I've got two electrons that are around it. Let's say now I move on to lithium. Now for lithium, that's number 3. I know that it has 3 protons. I'm going to calculate this for the 1s electron it has, and also for the 2s. It has a total of 3 electrons. It's 1s2, 2s1. So I'm quickly using the periodic table to determine what the electron configuration is. I think I'm going to have interactions between the protons and an electron that's in the 1s, protons, electron in the 1s, protons, and electron in the 2s. if I were to think about their effective nuclear charge, if I'm thinking about the effective nuclear charge for a 1s electron, there is no electron with a smaller principal quantum number for that. That electron doesn't have any shielding to it. But if I'm thinking about the one that's in the 2s, that's what I'm trying to designate with red there, there are 2 electrons that have a smaller principal quantum number. That's what I'm trying to show within this pictorial picture here. From the perspective of that 2s electron, there are 2 inner electrons that have a smaller principal quantum number. Those are shielding somewhat the positive charge. So in a sense, those are counteracting some aspect of the positive charge. So these would then be the effective nuclear charge values that I would calculate. They're different for a 1s versus a 2s. For the ones that are in the 1s electron shell, it's +3. For the 2s, it's only +1. This to me really is a depiction back to this analogy. 3 protons, that's talking about the light bulb's brightness. There's this frosted glass that surrounds it. And now the observer is this valence electron, this outside electron here that's in the 2s shell. It has a higher principal quantum number than the ones below it. Okay, before I go on right here, any questions for me? Tell me in the chat on this. This question here, Jacob has, so these equations are based on the electrons observing the nucleus. I would say that the manner of that observation is how are they experiencing the charge that's in the nucleus? We have opposite charges, positive and negative. So this observing is asking about that net attraction between the protons and the electrons after we account for the shielding. That's what we're doing when we're thinking about this observing part. Let me go on. I want to illustrate a few more points. So let's say we're looking at a 2p electron in neon and a 2p electron in argon. So here's neon and argon. If I were to set up and do the math for this one, I know the number of protons. I've got number 10 for neon, number 18 for argon. In both cases, I'm going to be asking about this 2p electron. This is how I'd set it up. So for neon, it's 1s2, 2s2, 2p6. From the perspective here of neon, there are 2 electrons that have a smaller principal quantum number. When I think about it for argon, 1s2, 2s2, 2p6, 3s2, 3p6. From the perspective of an n equals 2 electron, it also has 2 electrons that have a smaller principal quantum number. These would be the resulting effective nuclear charges on a 2p electron, whether I was looking at neon or I was looking at argon. How about the 3p electron in argon? This would be my setup for that. It has 18 protons, once again. From the perspective of that electron that is in an n equals 3 level, I would add up n equals 1 and n equals 2. That gets me a total of 10 electrons there. So for that one, it also turns out to be +8 for its effective nuclear charge. So what I'm trying to illustrate here is you can calculate the effective nuclear charge for any of the electrons. Second thing I'm trying to illustrate is notice how neon and argon both ended up being +8 for that outermost electron. Same value within that. We are going to see that that's true for the different columns that we look at. The different columns of the periodic table, they're going to be grouped based on the effective nuclear charge that they're experiencing. To illustrate that, let's say we look at fluorine here. I'll go down this column right here. So see if this makes sense. Fluorine has a total of 9 protons. For its valence electron, 1s2, 2s2, 2p5, 2 electrons are in a smaller principal quantum number. So the effective nuclear charge would be 9 minus 2, which is +7 for fluorine. How about for chlorine? See if you can calculate the effective nuclear charge for chlorine for me. For the valence electron. I see that I have 17 protons. If I write the whole electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5. So if it seems like I'm going through fast to get those, I can use a periodic table to quickly get that. And I see that in this case, I've got the same value for the effective nuclear charge, +7. Now, sometimes students say, well, can you also now just count over +1, +2, +3, +4, +5, +6, +7? Yeah, it works. Those different columns, they're really telling you the effective nuclear charge. How about if we go down one more for bromine? So the way that we do the math for this one, bromine's number 35. This would be its whole electron configuration. I've grouped these based on n values. And if we're interested in something with n equals 4, all of these count for being core electrons, inner electrons that have a smaller principal quantum number. So sure enough, for bromine as well, it's also +7. So we're really seeing something that Mendeleev, in a way, he found out based by grouping it on the properties, but we're getting some insight now and connecting it to the electron configuration. We're seeing that we can look at the effective nuclear charge on these valence electrons, and we see that it is a periodic trend. Here's the book's description where it's doing this explanation here, where it brings up what's going on for sodium, and we see the different, let's say, radio probability functions for where the electrons are found. If we look at this and we say, well, how does this now show up on the periodic table? Is there a pattern for the effective nuclear charge acting on the valence electrons? If I went right across there from lithium over, with lithium, I see 3 protons, 2 shielding electrons, so it's +1 for its effective nuclear charge. Boron would be +3. Oxygen +6. Neon all the way +8. In fact, when I reach my noble gas on the far right-hand side, my effective nuclear charge has reached a maximum. I see that the effective nuclear charge is increasing left to right for the valence electrons, and it reaches a maximum when I get to the noble gas. What happens after I go from the noble gas, like from neon, back over here to sodium? The trend has been increasing left to right, but what happens with sodium? Now I see that I have 11 protons, and I change the ones that I count as shielding. I now have a total of 10 electrons that are shielding. 1s2, 2s2, 2p6, all of those have a smaller principal quantum number. So notice how my effective nuclear charge has reset. It's back to being +1. This idea of something matching up for the columns and then resetting, that's what happens with a periodic trend. Here's this description from the book, a figure that I like from the book, where it's showing the effective nuclear charge, whether we're talking about a 1s electron or the valence electrons. If you look at the 1s electron, the effective nuclear charge on it, it just keeps going up, 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 up. The periodic table does not look like this, okay? The periodic table is not a line that is just a ramp that just keeps going up. The periodic table is periodic, means it goes for a while left to right, and then it starts over again. If you're looking at the effective nuclear charge for an inner electron in the n equals 1, it never resets. You just keep having more and more protons. There's nothing to cause it to get smaller again. That tells me that the periodic table has almost nothing to do with 1s electrons. Because look, it just keeps going up, 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 up all the way. That is not what Mendeleev's table is describing. It is describing properties that change and then they reset and they start over again. They're aligned with what we see for the effective nuclear charge for the valence electrons. That's why I say this is really a profound insight, how we see that the effective nuclear charge, core idea, well, no pun intended, crucial idea for explaining the periodic table for us. And we see as we go left to right for the valence electrons, it gets bigger and bigger, and then it resets again. And then it gets bigger and bigger, and then it resets again. One slight subtlety to this, don't let this part mess with you. We see that if we go down a column right here, the effective nuclear charge increases slightly more than we anticipate. If your first understanding is, if you know the column, you know the effective nuclear charge, that's great. Don't let this little subtlety disrupt that. I'll explain why a little bit more fully, but as my first goal is, I want you to be able to identify the effective nuclear charge and think about it for the different columns. So to sort of recap this part, if I'm calculating the effective nuclear charge for something like hydrogen or helium, really easy to do. I could write out the whole scheme right there, or I could just say, hydrogen here, 1 proton, nothing shielding, it's +1. Helium, 2 protons, nothing shielding at +2. Guess we got to be a little careful because below that, those noble gases were +8. But I think we can easily perform that calculation. When we were looking at lithium, we saw that there was a difference if we were calculating the value for a 1s electron versus a 2s electron. And beyond the calculation there, why are those different values? I think we can explain that. That's really a key idea of what is going on with effective nuclear charge. We see that for lithium, if we're talking about the 1s electron closer to the nucleus there's nothing shielding it. It's experiencing that entire +3 charge from the nucleus. But if we're talking about a 2s, we now have a shielding. We have that frosted glass. We have electrons that have a smaller principal quantum number that are leading to electron-electron repulsions and diminishing the charge that outermost electron would be experiencing. When we move on to things like sodium or potassium, I'd say both of those are back to being +1. We've reached a maximum with the noble gas, and then it's back to having, for sodium, 11 protons and 10 shielding electrons. For potassium, 19 protons and a total of 18 shielding electrons. Now, back to that one subtlety about how the column that you're in could change it just a little bit. I think within our model right here, for what constitutes the shielding, I think for sodium, there's 11 protons, there were 10 shielding electrons, so it ended up being +1. Same kind of thought here for potassium, but I'm drawing potassium larger because those electrons are in larger principal quantum numbers. The book's language here is that for valence electrons, going down a column, the effective nuclear charge increases slightly because the more diffuse electron cloud is less able to screen. What is that saying? It's saying that as this cloud has gotten bigger, where the electrons are found, it's not doing as good a job of blocking the charge for the outer electrons. More diffuse means it's just less dense. It's not as effective blocking it. So if I were to think about potassium here, instead of saying it was +1 for the effective nuclear charge, it changed just a little bit, might be 1.1, just a little bit. That's why I'm saying let's not have that be a major focus for us. Let's have our main attention be how it changes as we go left to right across the periodic table. So here I've got a couple different sort of learning outcomes on this. I'm curious, what do you think when it comes to effective nuclear charge? Could you use the periodic table and calculate the effective nuclear charge for a valence electron, for any electron? Could you explain why it is a periodic trend for valence electrons? Could you explain why it increases slightly going down a column? So this one right here, I want you to check all that apply. What skills do you think you have?
Am I able to ask a quick question?
Sure, please.
I don't really know how else to word this, but what exactly is being shielded?
No, it's being shielded is that we initially have a certain amount of positive charge in the nucleus, and that shield, it's not like we're somehow making the protons vanish. But what we're doing is, from the perspective of an electron that's outside of that, if there's other electrons between the nucleus and that outermost electron, it's diminishing somewhat the positive charge that that outer electron is experiencing. And the reason that's important is we're all about the way that we have protons and electrons being attracted to each other. And so what we're trying to do is quantify how much of an attraction is actually present there. We can't just look at the number of protons, because we have these other negative charges, the electrons, that could be in that region of space between the two.
Okay, so the valence electrons are shielded from like attraction to the nucleus then?
Yep, the attraction is being diminished because there's other electrons that are found between where they are and where the nucleus is.
Okay, and that reduces the positive charge of electrons?
Yes, now let me ask, you said that statement in probably the most questioning way possible. You said, I mean, your statement was correct, but you said it as if you were about as most uncertain as you could possibly be. Is that true? Do you see that? Because we have a certain amount of positive charge that's being diminished because it's being surrounded by negative charge. It's as if part of that positive charge, it's not like canceling it away, but it is diminishing it because we have some electrons that are in the way from the perspective of our outermost electron.
Got it. Okay.
Okay.
Cool. Thank you.
Yep. So within the setup right here where we're at right now, we're going to keep practicing this within today's class a little bit. This idea of what we're able to do. I see a lot of confidence here where it's first of all calculating the values. It's going down a little bit to explain it. I think the main thing that we want to have as far as a skill to be able to explain it here, I think is going to be on that third one. Explaining why the effective nuclear charge is a periodic trend. Let's see if we continue to apply it in class, if that becomes a little clearer for you. So let's begin to sort of play this out a couple different ways. And by play it out, I mean, let's see how the effective nuclear charge is influencing different aspects, different properties of these atoms. So here's one on the left-hand side. These are the radial probability functions that we have for hydrogen, that's shown in the blue, for a helium plus, which is pink, or a lithium 2+, which is shown in green. So I have either a neutral atom, a +1, or a +2. So I know what it would look like here for hydrogen. 1 proton, 1 electron. And when I say a simple shell model, I'm sort of using like what Bohr's model might be, how that would look. If I wanted to calculate the effective nuclear charge, I could do it for any of these. It doesn't have to be only for neutral atoms. We can calculate the effective nuclear charge for any electron in any atom, whether it's an ion or an atom or not. Now, in this case, if I'm calculating the effective nuclear charge, if I show our shell picture here, these are all just with 1 electron. These are what are called hydrogen-like. Hydrogen-like meaning that even though we've changed the number of protons, they still only have 1 electron that we're interested in. So if I were to calculate the effective nuclear charge on this, I don't think I have shielding taking place in any of these. There is no smaller n value electrons. So I would say my effective nuclear charge would be +1, +2, and +3. This would be for hydrogen, for helium plus, for lithium 2+. And now what I'm trying to do here is notice how these shells are getting smaller. The electron is being found in a 1s orbital, but closer and closer to the nucleus. And if we go back for these radial probability, that's what I'm seeing too. Hydrogen, and then I see with the helium plus, it gets pulled in smaller. Lithium 2+ gets pulled smaller yet. I'm seeing a really clear relationship between the effective nuclear charge and the distance the electron is found. As I have more and more positive charge, it's leading to a contraction. It's pulling that electron closer. In all of these cases, they're found in 1s orbitals. But notice how the 1s orbital is getting squished closer and closer to the nucleus. It's getting squished closer and closer to the nucleus because I have more and more protons there pulling it in. So in a way, this is sort of our first connection for how the properties are related to things like the effective nuclear charge. I think we can really easily explain why we have this contraction. We can explain it because we have more and more protons there. So when the electrons are found in the n=1 shell, that shell gets pulled closer and closer because there is a greater attraction present. I'm trying to explain phenomena like that back to the charges and the interactions. That's what we want to use to offer our explanations here in chapter 7. And I think let's begin with looking at aspects of the size. I think this one's going to be really helpful because once we have aspects of the size for different atoms and ions, it's going to be really easy to connect that to other ideas within the chapter. So I really want to focus our attention now of trying to explain and predict the size for atoms and ions. So first of all, it's a little bit difficult to say, well, exactly what is the size of an atom? Because they're not like hard billiard balls like Dalton had. Okay, we have an electron cloud. It's not exactly clear where an atom starts or where it finishes. So when they're calculating the size of it, sometimes the way that they do it is they say, well, I'm just going to figure out how when they bond together, what half that distance would be. This is not a crucial part of what we're up to, but I'm just pointing out that the atom size itself, it might not be that easy to necessarily determine for sure. This is the data though that we have that is showing two different ways, sort of the resulting pattern. So this would be the radius of various neutral atoms. So I show that it's the same data, but it's shown pictorially two different ways. Take a second, look at both of those features. See if you can identify patterns for what is going on. As I look at it, my dog, as I look at this bottom part right here, I see that as I go left to right on the periodic table, and what they've done right here is they've shown the first two columns and then the ones on the right-hand side. It's getting smaller as I go left to right. And then it increases in size. And then it gets smaller as I go left to right. And then it increases in size. And then smaller and then increases once again. That's the same thing that they're trying to show visually here. They show the size for hydrogen and helium, and then it gets bigger again for lithium, and then it gets smaller as you go across. Then it gets bigger again, and it gets smaller as you go across. So if I were to try to describe what this trend here is, it seems like if I'm going from the top of the periodic table down a column, the size is increasing. If I'm moving left to right, it's getting smaller. Those are the patterns. What would be the explanations for it? I think as I'm going down a column, I am increasing the principal quantum number, the n value for those outer electrons. I'm in n=1, then n=2, then n=3, then n=4. Those n values, those are the sides of the atomic orbitals. So if I'm going down a column, I am populating electron orbitals that are further and further away from the nucleus. If I'm going left to right, what's taking place? The effective nuclear charge is increasing. I'm not going to a larger n value, but the effective nuclear charge is leading to a contraction. So see if you can, mentally put these parts together. I'm in the same principal quantum number and I'm going left to right and there's more protons. Then I jump to a larger atomic orbital, larger principal quantum number, and then it gets smaller left to right as I have more and more protons present. Then it resets once again. That's what I have as far as my pattern for my neutral atoms. So if I'm looking at this one, this was our question that we posed right at the start. Which of these would be smallest? I think I can give a really good explanation and a comparison for the hydrogen and the helium atoms. I think helium is going to be smaller than hydrogen. Take a second, think to yourself, can you give a good explanation for why helium is smaller than hydrogen? I think in both cases, it's N equals 1, 1s1 or 1s2. But for helium, there are 2 protons. For hydrogen, there's only 1. That's made it so the helium is smaller. That's what I mean when I say, can we offer an explanation? Now, let's say we go from this, and instead of looking at neutral atoms, we're looking at ions. What would it be different when we go from the neutral atom to an ion? So as you know, we have both anions where we've added electrons and cations where we've removed electrons. Here's a couple ways of showing the different ones. So first of all, on this left-hand side right here, for these elements at the top, lithium, beryllium, sodium, magnesium, they're showing in gray what the neutral atom would be. And then in the darker part, those are the resulting cations. Notice for these metals, the cations are always smaller than the neutral atoms. If we look at the bottom, it's just the opposite. In the center are the neutral atoms, and then on the outside, those are the larger anions. Compared to the neutral atom, the cation is always smaller. Compared to the neutral atom, the anion is always larger. If we look over here on the right-hand side, you can really see the difference. Notice how the anions here are all much, much larger than we have for the different cations. A lot of times we've been looking at compounds like sodium chloride, right? Now we would see sodium chloride, those are not the same size. Look how the sodium ion is much smaller than the chloride. The anions are larger. So now let's take this and say, well, how can we explain this? So for all of these, you notice I'm trying to describe the phenomena and then step back and say, how can we explain this? Why would cations always become smaller? Well, the electrons are repelling other electrons. There's electron-electron repulsion. By removing electrons to make cations, I'm removing aspects of the electron-electron repulsion. That allows it to get smaller. The electrons with other electrons are leading to these repulsions. So by removing them to make cations, it's getting smaller. For the anions, just the opposite. Adding electrons are going to increase these repulsions between the electrons, and it makes it larger. That's my explanation for why cations and anions differ in size from their neutral elements. Now, when we're looking at variations in the number of electrons that we have and we're making these comparisons, many times we're going to do comparisons with things that are called isoelectronic. Isoelectronic, iso means the same. You've got the same number of electrons present. I think all of these are isoelectronic with each other. If you look at your periodic table, sodium plus, the fluoride anion, the oxide anion, aluminum 3 plus, magnesium 2 plus. Take a second, look at the periodic table there. I think they are isoelectronic and they all have the same number of electrons. Look at your periodic table, see if that makes sense. See if you can figure out how many electrons each of these has. When I use my periodic table within this one, I think that I've lost some electrons when I'm forming the cations, and I'm adding electrons when I'm forming the anions. I think in each of these cases, I've ended up with 10 electrons. In each of these cases, I have 10 electrons. In some cases, I've added, in some cases, I've removed. Notice, though, they all have different numbers of protons. They must have different number of protons because they started out as different neutral elements. They've all ended up with 10 electrons, but oxygen would have 8 protons all the way to aluminum that has 13. Notice what that does to the resulting size. In each of these cases, the electrons have the same electron configuration. They're all adding up to 10 electrons. But notice as you have more and more protons, it's getting quite clearly smaller and smaller and smaller. This is, to me, back to exactly the same idea that we were looking at. If we're looking at the same number of electrons, but we're changing the number of protons, it changes the size. This was true whether we were looking at our examples that were hydrogen-like, hydrogen, helium plus, lithium 2 plus. That was 1 electron, but different number of protons. This is 10 electrons, different number of protons. But we see quite clear how it leads to a contraction. More protons in the nucleus, bringing those electrons in closer. So now if I'm looking within this one, let's now see if we can explain this part, because I think we have a complete understanding now. So if we're trying to identify which would be the smallest, one thing that I find helpful is I wrote the information for what they each correspond to. If I'm looking for hydrogen or hydrogen anion, there's 1 proton in each case. One is 1s1, 1s2. For the helium or the helium plus cation, they both have 2 protons, different number of electrons. We've already compared hydrogen and helium. I think helium plus cation is going to be the smallest out of this group, and the hydrogen minus anion the largest. So before I offer my explanation here, I want to point out an aspect of this question right here. Notice within this question, there is a combination of neutral atoms. There's a cation, there's an anion. When we have questions within this chapter, I want you familiar with how we have patterns based on the periodic table. But I don't think there is a pattern on the periodic table that lists these, right? I think that we had to know what the phenomena is in order to be able to explain the difference here. I think the helium plus cation, I know it is going to be the smallest because it has the most protons and the electron is found in the n=1 shell. I think that B, the hydrogen minus anion, would be the largest because it has only 1 proton. Both electrons are found in n=1, and I have 2 electrons rather than just 1, which would lead to larger electron repulsion. That would be how I'd begin to offer explanations for the differences in the size here. Now, I've talked a little bit, and we'll practice that a little bit more in just a second. I've talked a little bit about what does it mean to make ions by adding or moving electrons. Let's see what's going on with that. So when we're making anions, we're always going to add electrons to make the anion to whatever energy level is available that's lowest in energy. So if I'm adding an electron to fluorine, 1s2, 2s2, 2p5, I could add the next electron to make the fluoride anion. You can see the spot for it. It's going to go and make it 2p6. When we're adding electrons to make anions, it's pretty easy. We just add it to the next available energy spot. Now, when we're making cations, we've got to be careful on this. Cations are always removed from the energy level that has the highest principal quantum number. And we have to be really careful here when it comes to our transition metals. Really common exam question on this. Really common exam question is making cations for things that might be transition metals. And the reason that we have to be careful within that is remember when we were populating to get to our transition metals, it was our 4s and then our 3d and then our 4p afterwards. Those were the different groupings. So if I look at iron, this would be the electron configuration for iron. Argon core, 4s2, 3d6. If I make it iron 3 plus, I'm removing 3 electrons. I'm removing from the 4s before I remove from the 3D. How about gallium? Gallium is right here afterwards. Take a second, see if you can come up with what you think the electron configurations are for iron 3+ and gallium+. I list what it is here for the neutral iron atom. See if you can figure those, and I'll share my work in just a second. So if I look at this one, what I'm going to be doing is I'm going to be removing from the higher principal quantum number first. For iron, if I'm removing 3 electrons, I'm removing both of the 4s because it's n equals 4. And then I'm removing 1 from the 3D. So I'd say iron 3+ would be an argon core and then 3d5. For gallium, I wrote out the whole thing that I had initially. And then if I'm removing 1 electron from that, I'm removing it from the 4p that I would have within that. That makes it gallium +1. So I'm pointing out within here, I know that's the most common error that students make when they're making cations. They fail to take it from the higher principal quantum number, and that becomes more of an issue when we're looking at things involving these transition metals. This idea of adding an electron, the energy associated with that is something we'll talk about next time, which corresponds to what's called the electron affinity. That's the energetics of adding electrons to make anions. This one right here of removing electrons to make cations, that's called the ionization energy. So next class, we're going to look at both of those phenomena, electron affinity and ionization energy. Now, I'm going to show you a couple problems here, and then I'm going to continue my discussion. But I want to show you the problems that are related to what we've been talking about. So here's one at the top where it shows you that analogy once again and ask, well, how would this apply if you begin to connect it to some chemistry ideas? So it's taking that same thing and asking now, how would it relate to different parts of the periodic table? This one at the bottom, which would experience a greater effective nuclear charge? The electrons in the n equals 3 shell of argon or the n equals 3 shell in krypton, which would be closer to the nucleus. That's what we looked at the start of class, where we saw we could calculate the effective nuclear charge for an electron in any atom. It doesn't just have to be the valence electron. This one right here, I filled up with a lot of really representative problems. Representative because they're asking us to do different things. In these first two at the top, they're asking us to use the periodic table and consider aspects of the size for neutral atoms. Notice in 7.28, it's asking us to explain. It's giving us what the values are, the ranking, and then it's asking, well, why? Explain what's going on there. That idea of offering an explanation, that also shows up at the bottom. 7.34, it says, make a prediction, put them in the correct order. But then in 7.35, it says, explain why, and it gives you then what the particular values are. Or it gives you the particular ranking, something that's bigger than something else. Explain why. So within this one, that's our objective. We want to be able to both make predictions and offer explanations. Effective nuclear charge is going to almost always be an aspect of that explanation. Let me show you how it fits with how we do this for some of these. So this was sort of our summary that we saw. We saw that when it came to the size, that it was increasing as we go from the top of the periodic table down because the principal quantum number was getting larger. We were populating larger atomic orbitals. And there was a contraction as we go left to right because we weren't changing the shielding, but we were adding more protons there that was increasing the effective nuclear charge. So if I were to look at these questions like 7.25, it asks, okay, arrange these different groupings based on the periodic table. So look at this grouping right here with fluorine, oxygen, and nitrogen. I see that nitrogen is the largest and it's getting smaller as I move towards fluorine. So let's see if we can explain that. Why does it get smaller as I move left to right on the periodic table? I'm increasing the number of protons. I am not changing the shielding electrons. So therefore, the effective nuclear charge is getting larger. The effective nuclear charge is getting larger, and it's leading to a contraction as I move across that set of the periodic table. How about this group right here? It's asking for ones where it's not quite as easy. I see beryllium, aluminum, and silicon. What would be a way to make a prediction on this one? This would be one very typical exam question when you'd need to make a prediction. In order to make a prediction about the size on this one, let's think back to what the aspects of the explanation are. We saw that we had a contraction as we move left to right, and then it gets larger with a larger principal quantum number, and then a contraction once again. So what we find within here is the smallest would be beryllium. It gets progressively smaller and smaller. It jumps up larger, and then we see a contraction once again. But that would be my explanation for here. The reason beryllium is the smallest, it has the smallest principal quantum number. The reason silicon is smaller than aluminum, that would be explained using aspects of the effective nuclear charge. When I'm talking about these, I think it's not like memorizing just one simple thing. It's looking at the relationships for what's there. Because I'd say in this case, if I consider hydrogen and helium, these are atoms that have a pretty small effective nuclear charge, and they have a small size. So what's going on within this one? The effective nuclear charge in hydrogen is just +1. In helium, it's +2. But if I look in terms of the size, those are my two smallest that I have in the whole group. Why is the effective nuclear charge not telling me the whole story? Because those electrons are found in n = 1. They're found closest to the nucleus. The atomic orbital is the smallest. So in this case, these would be, we see the two smallest ones there. It's because they're in n = 1 for their atomic orbital. This group right here, hydrogen, lithium, sodium, all of these have roughly the same effective nuclear charge. But notice how they're quite different in size. How do I explain this? They're populating n = 1, n = 2, n = 3. So I would explain this because they have different principal quantum number. If I moved across this one, these atoms have the same principal quantum number, but they have a different size. How do I explain this? I say that they have differences in effective nuclear charge that's leading to the contraction there. So what I'm trying to point out within this one is when it comes to explanations, we really have to think big picture about what the phenomena is. It's not just memorizing one specific thing. If they give you what the particular value is and ask you to explain it, to me, it comes back to what is the charge acting on that electron? And by charge, I mean, what is the effective nuclear charge? And second is, what atomic orbital is it filling? Both the effective nuclear charge and the principal quantum number, both of these influence the size. I think the size is one of the most important properties that we're going to have, because we're going to see that it really easily connects to things like the ionization energy next time. Here's one where they give me some values, where they give me what the ranking is, and they're asking me to explain it. Take a second, see if you can put together your own explanation for A and C. Why do we see these rankings for A and C? If in your ranking, you're thinking things about the number of protons, you're thinking about atomic orbitals, you're thinking about how many electrons you have, those are exactly the kinds of things that we want to be thinking about. If I think about both of those, if I do a comparison across A, I have the same number of protons in each of those. But remember that the electrons with other electrons cause repulsions. So if I have more electrons, it's larger. If I have fewer electrons, it's smaller. With fewer electrons, I'm decreasing these electron-electron repulsions, and I see how as the charge gets more and more positive, they're getting smaller and smaller. So I think in a way I have the same explanation there for both A and C. How about an explanation for this set within B? What's going on there? Here they are on the periodic table. Within this one, I see that I have differences in the principal quantum number. These were filling in with, initially they were n equals 2, 3, 4. They've all become +2 cations. They all have different principal quantum numbers that they're filling, and that leads to differences in the size. So I'm really trying to stretch our different ways that we can think about these explanations and try to show you the diversity for what's going on. This would be another example. After I've taken these when they become +2, they end up being isoelectronic with helium, neon, and argon, and they have differences in their atomic, the N value. So I know within this one, towards the end, I was doing a lot of talking because I was trying to bring up the kinds of explanations that we would offer. What our plan is next time, we're going to see how, once we have, I think, a pretty good understanding of aspects of size, how we can quickly use that to explain the other parts of the chapter. This other parts of the chapter, that's going to be pretty quick for us. That will be roughly half of the class time. And then we're going to begin to look at some of the ideas at the beginning of chapter 8 then. Chapter 7's really quick. Most of the stuff in chapter 7 were things that we discussed tonight, looking at aspects of effective nuclear charge and how that was then leading us to make both predictions and explanations for size. I think between the comments people were making within the pre-class video, which was great, what we talked about tonight, if you double back and just review that, skim the discussion within the textbook, I think you're going to have a really great setup to get rolling within chapter 7. Okay, that's all I got for you. I'll hang around if you got any questions. As always, I appreciate your attention.
I have a quick question just about the next exam, which I know is pretty early to ask, but when you're talking about giving explanations, will we be asked to write short responses on this next exam?
No, good question.
Okay.
They'll all still be multiple choice. And so the explanations will be a lot of times the same kind of things that I was just bringing up. So it will still be multiple choice, but you notice within here, there's a lot of variety for what could be going on, right? It could be explained using effective nuclear charge. It could be explained by what the principal quantum number is, different things like that. So they will remain multiple choice, but you would have to sort of evaluate the different explanations.
Okay. And then I'm like kind of still stuck on this idea of like reducing the positive charge or so in this last example that we did of the calcium ion, the magnesium ion, and the beryllium ion, what I wrote for my explanation was that the difference in quantum numbers and the number of orbitals was the reason for the size change, so that in higher orbitals there are more core electrons to shield the electrons from the nucleus. So that would then decrease the positive charge.
I think you're going off a little bit on that, because let's say we were just looking at neutral atoms here. If we're looking just at neutral atoms down a column, let's say I'm comparing beryllium, magnesium, calcium. I think those all have roughly the same effective nuclear charge. I think they're all in my column where I would be identifying a effective nuclear charge of +2. They got there in different ways, right? They have different numbers of protons, different number of electrons, but based on the periodic setup, I think they've all ended up with the same effective nuclear charge. The difference in the size then, it can't be based on the effective nuclear charge. It must be based on the orbitals that we're putting them in n equals 2 versus n equals 3 versus n equals 4. So it wasn't the charge that they were experiencing. It was the orbitals that they were originally placed in.
Okay. So it's just that, like, it's just the amount of core electrons that then leads.
In that one, I don't think I would work any harder than to say, going down a column like that, they have the same effective nuclear charge, but the valence electrons are being placed in larger and larger orbitals. N equals
Okay.
2, N equals 3. I think that's all I need to explain that trend going down a column.
Okay. Perfect. Thank you.
If we're talking about atoms which are isoelectronic, like let's say, for example, O 3 or 2 negative, right? Anion. Are we going to, is the size, it's not going to be the same as neon still, right? Like,
well, I think correct, because if we get to the same number as that, but we've changed the number of protons, right? So we have the same, we're making apples to apples comparisons, that we're talking about the same number of electrons that are found in the same atomic orbitals. However, we've changed the number of protons. It's a different number of protons. So the apples to apples part is it's the same number of electrons. But if I have more protons, then it would lead to a contraction of that apple cart. It would lead to a contraction of those electrons that are present.
Okay, and then if it gets ionized in a way that changes the principal quantum number of its valence electrons, is that going to change the size much more drastically?
Like what kind of example? Like if you're, let's say we're doing a comparison right there. So we were comparing oxygen in neon, and then let's say we put in sodium plus. Sodium plus would be another way to get to that same number of electrons, right? That would be sodium plus within that one. That would be even smaller, because now I'm once again isoelectronic with neon, but I've got even more protons present. If I were to take it, let me double back, because we actually had some data where right here, where I think the key difference right here, simply the number of protons. And we see how adding more and more protons within our comparison for the same number of electrons leads to a contraction right through there.
Okay, and then, so let me just think for a second. So, okay, a higher principal quantum number is always going to be larger than a lower one, regardless of the L value.
When you say the L value, you're thinking now comparing when we have like an S and a P orbital?
That's
right now, yeah. Right now, we can get more sophisticated with what our shielding and stuff is, but right now, our simplest approach, we will simply be looking at our principal quantum number. We'll just be looking at N to use that as the main thing that determines the relative location of electrons, whether they're inside or outside other electrons. You are correct. I would say that a 2s is slightly closer than a 2p, but for our first analysis, we're going to say that doesn't really matter. It's far more important if it's N equals 2 as 2s and 2p versus N equals 1 like a 1s.
Okay, so just the two main factors in determining the size is going to be the number of protons, and then the highest, is it the highest principal quantum number, or is it
Yep. The ones that, because I mean, when we're talking about the size, we're talking about the electrons that are on the outside, the outermost electrons. So we're interested in what atomic orbital they are in.
So even though, okay, so it's not really correlated to the order that the electrons are added, which ones are farthest out, right? Because if you say like 4s that comes before, it's added to,
Yeah,
it's added to 4s before 3D, but 4s
yeah,
is still on the
I mean,
outside.
recognize that when we're talking about the order that they're adding in, an atom, it doesn't know what the previous order was. Meaning, you know, if you're scandium, a scandium atom doesn't know, hey, I got one more proton than calcium, right?
Okay, yeah.
It just know, if it knows anything, it should say, no, this is the arrangement for that number of protons and electrons. This idea of seeing a progression as we move along, I would say that's just us as humans trying to see what comes next in the order. But, you know, for any of these, if you're scandium versus calcium, you don't know that, oh, I'm just one more than calcium. It is just the energy corresponding to the particular protons and electrons and their interactions at that moment.
Okay, so just like the reason why potassium, for example, is much bigger than argon is just because it gets added to the next biggest.
You got it. We've added to a larger principal quantum number for the outer electrons, and those are the ones that we're talking about for the size.
Okay, that makes sense. Thanks.
On the chart, can you explain why copper and silver like increase?
Let me see. So was that a size one that you had?
On the periodic table chart that shows the different sizes.
This one right here?
That chart. It shows that copper and silver increase. Can you explain that?
Excellent question. Now, with a lot of these, I find that if you've got a PhD in chemistry, I can explain it. I might not be right, but it's going to sound like I know what I'm talking about. And so what I would say, what I know what I'm talking about on that one, I would say something along the lines of, oh, well, you know, with copper and also with silver below it, those are both anomalous electron configurations. What we've done is we've shifted one, and instead of being the 4s, we've shifted it over, and now it's getting us to 3d10. And because of that, it's resulting in more electron-electron repulsions that is somehow leading to a larger size. Now, am I right? I got about a 50% chance of being right on that. I think within that, I think it's got to do with something with the anomalous electron configuration. And because it's larger, it's telling me it has to do with the interactions of the electrons that I have, which must be leading to more repulsions. That would be my way I would tap dance and try to come up with an answer for you. Okay,
that makes sense.
Yeah, it does make sense. I don't know if I'm right, but it makes sense.
Yeah. Is that something we would need to worry about for exam number 3 or whatever?
No.
Okay, thank you. I appreciate it.
Yep.
For how electrons are added or taken away in ionization, so it's not going to be. It's for anions when they're added. It's always going to be the one. Like it's just if you were going to the next element, basically, unless it's an anomalous configuration.
Yeah, it's just going to the next spot within that, and so that's usually pretty easy for us to figure out where the next spot is going to be. And when I say the next spot, a lot of times if you draw, if I think about it with like an orbital diagram with the one with like the boxes, it's pretty clear usually of, oh, well, where is the next box that I'm going to be adding an electron to? And most of the time when we're adding those, the ones that we're making anions of, they're usually in this part of the periodic table, right? There are nonmetals. So it's usually pretty clear where the next electron would have to go.
Okay. So if they're taking, like, let's say iron is made into a cation, and then you add them back, are they just going to be added back in the reverse order that they were taken away?
Yeah, I think they have to be. Yep.
Okay. All right. Thank you.
Sure.
Hey, Dr. Clark.
Hey.
For like the lithium examples, I was just confused as to like, so if we're asked to calculate like the